Welcome back. This lesson is going to be about the difference between the normal distribution, which is what we're looking at now, and the standard normal distribution. So as we've seen, this probability density function can have any value for the mean and any value for the standard deviation. I've set the mean of 3 and the standard deviation of 2. As I've shown you before, we can have areas underneath the graph under various intervals. Now let's set the value here at the mean. So there's the upper limit at 3, and let's set the lower limit here at 1. Where are you? 1, there you are. Now the difference between these two equals the standard deviation. So as we've seen before, if we go from the mean down by 1 standard deviation, we have about 34% of the area under the curve, or a probability of about 34% that the score would lie between 1 and 3, given this distribution. Now what about other distributions? Let's see what happens if we go and have a mean of 5 and a standard deviation of 3. Let's put the upper limit at the mean, and let's put the lower limit this time at 2. So we're still moving from the mean downwards by 1 standard deviation, and we find that the properties of this curve, it's still, even though it's a different shape from the one we had a moment ago, we still have 34% of the curve between 2 and 5 representing a difference of 1 standard deviation. The standard deviation seems to be a natural unit for measuring distances away from the centre of the curve, and in fact that's exactly the idea behind the standard normal curve. Now this is a difficult function to integrate. If it's not straightforward at all, and the prior to well, pretty much all of the tables of these things prior to calculators, we had things like this to look at. So this is a table. Now, could you imagine computing that table? Obviously, by hand it would take years, but with a computer, of course, it'll take moments after you've programmed the computer. But the thing is, are you going to want to compute a table like this for every different possible value of mean and standard deviation that exists? No, of course you're not. So it was decided very early on that we should standardize this curve to have a mean of 0 and a standard deviation of 1. There it is. This curve now is called the standard normal curve. Now it's just like any other normal curve. It obeys the same function that we've got here, except that sigma equals 1 and mu equals 0. And now these limits a and b will tell us exactly. So if I put b equals 0 and if I put a at minus 1, I am 1 standard deviation away from the mean. Once we have a standard normal curve, we no longer refer to the horizontal axis with x as a continuous variable. It's still continuous, but we refer to it as z to distinguish that this is the standard curve rather than any of the other infinite variety of normal curves that were out there. So we would say that a z-score of minus 1 represents 1 standard deviation lower than the mean, and as we can see, the familiar 34%. If I drop down to minus 2, if I can stop there, I end up with 47%. Now of course there's nothing to say I have to stop at minus my upper limit. My upper limit could go from plus or minus 2 standard deviations, or plus or minus 2 z-scores, and I would have 95% of the population, if it was a normally distributed variable, within that space between plus or minus 2 standard deviations of the mean. If I go to 3 standard deviations above and below, I get almost all of the curve. There's a tiny, tiny, tiny little bit there which is still not accounted for. But to all intents and purposes, 99.7%, I've got just about the entire population covered if I go plus or minus 3 standard deviations from the mean. So this is the advantage of the standard normal curve. Prior to computers and calculators being everyday objects, we would need to use tables, and this is the standard normal probability. Notice the Z there for the Z-score. If I go from the tables were always set out to be from negative infinity up to a particular point. So if I go to find a Z-score of 0, then it's 0.5. Let's take a look at what that would be like. So a Z-score of 0. Now, when they did these tables, like I said, the lower limit was always, I've set mine at -5, which is close enough to the edge of the distribution, and the upper limit of 0, so that's the Z-score of 0, 0.5 of the graph has occurred to there. If I set B at +1, then as we saw in one of our earlier examples, we've got 0.5 on the left of mean and 0.34 on this side, so 0.84. Let's go and check that table once more. If I find a Z-score of +1, there it is, it's 0.8413, which is what we're looking at, 0.8413. So we used to use tables to do these things. You're so lucky these days you have calculators to do them. And the calculator, of course, well, it can do this as well. If I pop into my calculator here and I say I want in fact, let's just use this one as an example. If I say I want a lower value here, so I've got a mean of 80 and a standard deviation of 20. If I want a lower value of 60 and an upper value of 100, so I'm 20 below and 20 above, or a Z-score of plus and minus 1. When I draw this, notice that it says the Z-scores here rather than the raw values I gave it. Lower Z is -1, upper Z is +1, and there's the familiar 68%. So if I just tidy this graph up a little bit, there's the familiar 68% on the calculator and on GeoGebra. So the calculator will automatically take the mean and the standard deviation you give and the upper and the lower boundaries and convert them to Z-scores before it calculates and draws these things. That's because the calculator has all these things stored inside it as a standard normal curve rather than any of the other normal curves that exist. Well, that's a nice little introduction, I hope, to get you a clear view of the difference between a standard normal curve and just a normal curve. Thanks for watching.